Hello, today we're going to start section 10.2. This is about confidence intervals. So, first of all, what are confidence intervals? Suppose we are given a population and we want to estimate, say, this is population of students. Let's say we want to estimate height, mean height of the students in all population. Now, usually, as we talked in chapter 1, it's very difficult to collect the data from the whole population. So what we do is we take a small sample and we ask the height from that sample students. And using the mean of that sample, we say we can estimate the mean height for the whole population, right? That is mu. For the sample is x bar. So using x bar, we are trying to estimate the mean height of all the students which we are talking about. Now, instead of just talking about estimating the mean, if we can say it's better, even better to say that we are, say, 90% confident that the population mean will lie in a particular interval. So instead of telling that we have a specific mean that is too difficult to say, we have to give a range of the numbers that the mean of the population will lie between those two numbers. That's a better option. So that is called confidence interval. Instead of giving an estimate, we are trying to find a range of numbers and we say that mean will lie within these two numbers. So for that, we are gonna need to know Z alpha. I think we already covered this in the class, so I'm not gonna continue with that, but please make sure that you know what Z alpha is and how to calculate that. You don't always have to calculate, most of the times it will be just given in the table of the values in the formula sheet. So, but you should know what that means, what Z alpha is. So please go over the first few slides. I already covered this in the class. So what we're gonna build up to now is the confidence interval. So what we did in the previous chapter, we learned about the central limit theorem. We learned that estimate of population mean will be normally distributed regardless of the shape of the population, as long as the estimates are delivered from sufficiently large samples. So if you're taking large samples, then the sampling distribution of sample means was supposed to be normal. That was central limit theorem. We can use that, right? Because then it's better to use normal distribution. In particular, the empirical rule also tells us that 68% of our estimates be within one standard error of the correct value. So what's happening here? We are saying that this the sampling means distribution is always going to be normal with your sample mean at the center. So if we have a 68% interval around the sample mean, then 68% of the sample means will lie within one standard deviation. This is one standard deviation less, so mu minus sigma, mu plus sigma. So 68% of the sample means are lying here, right? So what does that mean? That means if around this was the sample mean, around sample mean, if I'm trying to find an interval by subtracting one standard deviation and adding one standard deviation. Now, you see how interval came to us instead of one number estimate. If we have this interval, then 68% of the sample means will lie in between. So there are 68% chances that our interval will contain the true population mean. That we can also say it like this, right? There is 68% chance that our true mean will lie within the interval, this interval, confidence interval. So we can call this to be a 68% confidence interval in a sense. So for example, if we draw like this is the sampling distribution of all sample means, and this we are drawing this around our sample estimate, right? So if we have one standard deviation less and one standard deviation more, then between this is 68% and outside is how much? That is total 32%. So one side will be just 16%. Both these sides are 16%. So what we are trying to say here, that if we take any interval, let's say around the sample mean, let's say we take this, it will contain the true parameter. Let's say this will contain the true parameter. Sometimes if the interval is outside that area, it will not contain the true parameter, that is the population mean. If the interval is coming outside here, it will not contain the true parameter. If the interval is here, it's not containing the true parameter. So how many times if you can find an interval, it will actually contain the true parameter, the true population mean? It will be happening 68% of the times, because 68% of the sample means are lying in between one standard deviation, right? So we can say if we can add and subtract one standard deviation from each estimate, about 68% of the relative resulting intervals will capture the population mean. So what we are trying to say basically is that if we keep on, this is a population, this is a small sample. From the sample, I take a sample mean. Let's say the sample mean is here. I subtract a standard deviation from it and add a standard deviation from it. I keep on doing this. I take another sample mean. Let's say the sample mean is a different value, let's say 2, and this is coming somewhere here, and I create a standard deviation less and a standard deviation add to it, and I keep on repeating this process multiple times. How many times these intervals will actually contain the population mean? 68% times. That is the confidence level we are going to translate to. Okay. So here is an example. Alice and Bob try to estimate the mean height of Math 1680 students by collecting the separate samples of size 30. Suppose that we obtain a point estimate. What is point estimate, first of all? Point estimate is if you are taking a small sample, the sample mean is called the point estimate for the population mean. Okay, so sample mean is called the point estimate for the population mean. We are trying to estimate, we are trying to guess what your population mean would be, and that is happening using your sample mean. Okay, so they are taking a sample size of 30, so n is equal to 30. And suppose that Alice obtained a point estimate. Alice took a sample and sample mean for her came to be 66.4, and Bob also took a sample size of 30 and the sample mean for him came out to be this. Now we know the standard deviation. Let we about this is about height, right? So you guys remember the standard deviation was 4.56. In this actually we know the population mean also. So using the standard deviation, we know that the sampling distribution of all sample means will also be normal. And you remember the standard error in that case for the sampling means was coming to be sigma divided by this, right? So we divide 4.56 divided by square root of 30 and we calculate that. Now, whatever that number is, I'm Alice subtracted that number. For Alice, the sample is this. she's gonna create an interval by subtracting this number. Let's quickly calculate that. This is 4.56 divided by square root of 30. I get 0.832. So she subtracted 0.832 and she added this number to her sample mean too. So she got an interval, right? So she's trying to guess my sample mean would lie somewhere in this interval. So let's say what that interval is. That is coming to be 65.57 to 67.23. Now, what is Alice saying? That how many times the sample mean will come in this? This is one standard deviation away from the sample mean, right? So she's saying that 68% of times the population mean will be in this interval. Okay, that's what we are trying to say here. Similarly, Bob also calculate 64.3. He adds 0.83 and he subtracts 0.83 and he gets this interval. So Bob's estimate is that 68% of time, all the mean height of all Math 1680 students will lie in this interval. So do you think which interval actually holds the population mean? So if you notice that 65, we know that for this case, usually we don't, but in this case, we actually have the population data and we've calculated this number, right? This is the population mean height. This is lying in the Alice's interval, but this is not lying in the Bob's interval. So Bob's interval did not truly hold the population mean, but Alice's interval did capture the true mean height. So how many times it will happen usually? If we repeated this experiment many times, how often the resulting interval will capture the true mean? That is 68% because we went one standard deviation away from the sample mean.